So there's a lot of records that we already know about. There's a couple more, and one of them is of particular prominence. Let me go over here to my DNS server. You'll notice that on the zone itself, so if I go to the zone, you're going to have what is called a start of authority record, an SOA. If we open up the start of authority, you'll see that we have a serial number. Now, when we get into zone transfers, which has just been added to the exam, they'll talk about how you can have a primary DNS server that has a read-write copy. That's the one that you update. And then I can replicate that to secondary servers. These secondary servers are read-only. And what they will do is occasionally, and in fact it's based upon the refresh interval, so every 15 minutes, the secondary server is going to go to the primary server and say, hey, what new records do you have? Now, initially, when I first say, hey, point it over there, I have to allow this particular server to be able to do zone transfers. And by default, it's not allowed. So you can't do zone transfers. So if you have a secondary and you say, hey, go to this primary server and pull down a copy, by default, Microsoft's DNS says, no, we're not going to let you do that. So what you have to do is you have to say allow zone transfers. You can say any server, only servers that are in the name server tab, and then only the following servers you'd put in the name and IP address, and those are the only ones that are allowed to pull from that. So SOA is where you would also go in and say whether or not we're going to do zone transfers. Now, this says how often you do a zone transfer. Every 15 minutes, I'm going to check for updates. But if you don't respond to me, hey, I want to do a zone transfer, and I don't get a response back, I'll wait 10 minutes, and then no response, 10 minutes, no response, 10 minutes, no response, and I will do that until I get to the expires. And so after trying for a day to get that zone transfer so I can be a secondary for the evilhackerempire.com, I'm not getting anything, so that secondary DNS server will delete its copy of the zone. It'll no longer host that zone record. It'll no longer be authoritative for it. So that's what we have that. Here you have the TTL. Now I want to show you this real quick. If I go under View and I turn off the advanced settings, when I go into the SOA, it still has a TTL, and the TTL is set for 1 hour. This is days, hours, minutes, and seconds. It does it on 1 hour. But if I go in and look at an individual record, you notice it doesn't have a TTL. It does. It's going to use a start authority TTL, or maybe we have it customized. So maybe I just need to update this TTL, but I don't see it. What I do is I go into View, I go back into Advanced Options, and then when I open it up, I will see the actual TTL. Now before, it was set for an hour. Now it is set for 20 minutes. That's what we have. And it shows you the timestamp last time it was updated. So we can do that as far as the SOA. Now PTR records, that's where we have a reverse lookup zone. In other words, I match the name, or instead of matching the name to an IP address, which is a forward lookup, I'm going to match an IP address to a name. So an SMTP server said, I'm irs.gov server 25. I'm going to go to irs.gov's DNS server, and I'm going to do a reverse lookup zone. So let me make a brand new zone. We'll say that the supposed irs.gov that I'm going to host, we're going to make it a primary zone, read, write, copy. And we have replication. We have all of that. I'm going to put in the IP address. Now, the machines that we have this information for to send out email, we want to verify that, or we want to say, oh yeah, that's ours, that they're going to come from an address of 131.107.2. Actually 131.107.2. And that's going to make a reverse lookup zone. Now, it used to be that you'd have to do what's called an inverse record. That's this guy right here. What they do is they take the IP address and flop it on its head. Let me illustrate the point here. When you have an IP address, we'll have, for example, 131.107.5. something. So we're going to say this entire subnet. If we go to www. Or we'll just say server 25.irs.gov, they approach the resolution backwards. So this is the network portion. But an IP address is a combination of the network portion where everybody in that subnet has the same network portion, but you also have a host portion, and that host portion is going to be different for each host. So here it is broader to most specific going that way. So as you move further this way, it's sort of like a phone number. You have the area code, you have the calling area, the local calling area, and then you have the client ID. So it gets more and more specific the way you go down this way. Here it's the exact opposite. This is really large. This is a little bit tighter. This is a lot tighter to identify. So the way that DNS does is it will try and flop this IP address backwards so it matches the same order where it's most specific on the left, least specific on the right. And what it does is it swaps the IP address 5.107.131, and then it adds a special extension, which is in address ARPA. Instead of me typing it, let me show it to you. So 131.107.2, they flop that around and then add .in address ARPA. And you used to have to do this with a text editor, but it'll do it for you. So you just put in the IP address, 131.107.2. I say next. This is for updates. We'll talk about that. I'll hit finish. And now I have 131.107.2, but it's done backwards. Now what I want to do is I want to make a reverse lookup record. So I will go in here and I will say this is going to be a PTR record. We'll tell it the host name they're going to send it to, and I will say mail.evilhackerempire.com, and that would be the I'm putting in the IP address. We're going to say that this is .6, for example. So now we have 131.107.2.6, and that puts it in the entire IP address. Or I could do it by a host name, and I could say this is going to go to we want to do server 25. 25 dot, what did I say, irs.gov? So it'll match it. So I say I'm server25.irs.gov, and I have this IP address. That machine will say, hold on a second. It'll go up to whoever is authoritative for irs.gov, which I'd have registered to have his own file. And then it'll say, all right, well, we're looking for IP address 131.107.2.6. It flops it around. So it's 6.2.107.131 in address ARPA, and it is going to match to that name. So in that case, it's proven, sort of, it's not DKIM or SPF or anything, but it's proven that my name actually matches to an IP address that is hosted by whoever is authoritative for the irs.gov. Now, authoritative means that I supposedly know all of the addresses out there. If I go to Microsoft.com's DNS server, they know everything Microsoft.com. If I go to Apple.com, they know everything Apple.com. I'm not going to go over to Bob's DNS server to resolve Apple.com. But how do I know where the Apple.com name server is? Well, we have another record known as an NS record. The NS record is going to list your name servers. So right here we have the name server, and I am listing it by name. So the name server is going to be vmm23.london.evilhackerempire.com, and then I would have to have an IP address that matches it. So anytime that I'm trying to resolve a name, I want to go to stormwindlive.com, I want to go to Microsoft.com, I want to go to Apple.com, what I'm doing is I'm asking the internet, and we'll show you this process, I'm asking the internet who is responsible, who is authoritative for evilhackerempire.com, and then it'll give me the list of all the name servers. And by the way, the SOA record for secondaries and the list of name servers, trying to find out where the name servers are, it's come to my attention somehow that CompTIA is very interested in knowing that you are very familiar with NS records and SOA records. So just be aware that this is definitely possibly exam worthy. And that's the last one that they have on there. Now there's all sorts of other records that I could put in. They just have tons and tons and tons. And a lot of these are not necessarily used on everything. You know, signatures and well-known services and route through and all that. So if you have a need for it, the record's there, but the ones that they want you to be familiar with, they have listed in here for you. So pretty cool. Let's go ahead and do a packet sniff on a DNS query. So here we are going in, and notice that I have my MAC address. He's running this on VMware. His destination is going to be another VMware server, and we have the MAC address for that as well. Now my source IP address 192.168.133.2, and notice that the destination is 192.168.133.147. How does my machine know that IP address? I've been told that's the IP address of the DNS server. That was either given to me as an option, as DHCP, or it has been manually configured. You don't just automatically know where your DNS server is, so it has to be in there. Notice that in this case, we're using UDP. DNS is kind of unique because it uses both UDP and TCP. The advantage of UDP is it's really, really quick. So I'm going to say it's going to be UDP, and notice that my source port number is going to be 53. My destination port number is going to be an ephemeral port number that I'm going to try and go through and to communicate. So inside the DNS server, I would send it. Now, what this is it's a decode. This decode, it means, or not a decode, it is a response, which means I've sent the query to the DNS server. This is the response back. That's why the source port is 53 and the destination port is this weird wackadoodle number. This weird wackadoodle number is what is called an ephemeral port number. An ephemeral port number. Now, the way that ephemeral port numbers work, let's say that I have a browser. And on this browser, I may have like 900 billion tabs open, and all these 900 billion tabs will pretend is going to the same web server. Now, the web server, we have to be able to differentiate the different streams, the different tabs. And in fact, inside the page itself, on one tab, I may have part of this that is going to grab the HTML document that defines everything. That HTML document may have like graphics that are stored somewhere else, like the little Facebook icon. That's actually stored by Facebook. So you can click on it and, you know, post the fact that you are doing something. That's coming from a different server. So you may have all sorts of different queries that come in. But let's say that all these queries are going to the same server. So on this tab, I am going to say that the destination is port 80. And in fact, all of these queries, because I'm using HTTP, is always going to be going to port 80. It's going to have the same source IP address, me, the same destination address, the web, but to differentiate it, we use an ephemeral port number. So the destination port is going to be port 80. The source port number is going to be something higher than that. And if we go in and look at the decode again, you'll notice that it's using 53,870, port 53870. That is what differentiates this particular stream. So I could be doing all sorts of queries with all sorts of tabs, but each of those tabs and each of those elements that are separate GET requests, they're going to have a different ephemeral request for it, and or a different source port number, and that's when the server sends it back. It goes from its well-known port, for example, if it's a web server, this would be port 80, but it goes to that ephemeral port, and that links that web socket. Source IP address, destination IP address, port number, source port number, destination port number, and protocol. That's called 5 tuples. So IP address, source and destination, port number, source and destination, and then the protocol. And that's how we keep track of which particular communications path we're using. So all of these requests will have different port numbers as far as the ephemeral port number, and that's how it differentiates. Now this is a response. So it said, okay, we had no problem with your query. What's going to happen is you're looking for lamley.com, www.lamley.com. This is going to be an A record. And here is the answer. Well, it's not actually an A record. It's going to be a CNAME record. And it goes from www.lamley.com just to lamely.com. So a lot of companies are getting away from having to put www on the front, and instead of having it fail, they'll just have a record that swaps it around. A CNAME record. Oh, www actually corresponds to this guy. So it'll say it's a CNAME record. Here's my TTL. Then we are also going to resolve the CNAME record for you, because that's, trying to get to that IP address. So I'll say, all right, well, who's lamely.com? And in this case, we do have an IP address, and it is an A record. Now notice again, it has a time to live. So if I'm doing a query and I say, hey, I want to go to www.lamely.com, I do the get, it actually redirects me, or instead of www.lamely.com, it redirects me to lamely.com, and I pull down the main page, but I also want to grab this graphic from lamely.com, this one from lamely.com, this one from lamely.com. However, as long as I can do that within the next 5 seconds, and how long does it take to load a web page? Milliseconds sometimes. I would be able to do that without having to do a DNS query for every response. So that's why you have longer TTLs, because it reduces the number of requests that we have to send out. But it's UDP. Hey, where's lamely.com? Here's all the results, and then I forget about you. But you remember me based upon the time to live. So that's how the decode works. Now over on page 158, they do show you the query, and it's just saying, hey, I'm looking for this address. And then on the bottom, figure 5.17, they show you this answer on here. So how does the stuff get into the DNS? Well, you saw me go in and statically configure some things, like VMM23 London. That is statically configured. As administrator, I went in and statically configured it. The problem is I have thousands and thousands and thousands and thousands of machines. And now externally on my publicly available DNS server, I don't want all my internal machines registering it. So anything that is public, I tend to lean towards static configuration. That's not only the IP address, but it's also the DNS records. Because as a hacker, if I can get access into your DNS, I own your company. I own your entire network. Because if I can get people to ask me what the IP addresses are, as opposed to your DNS server, I can do a man-in-the-middle attack where I'll send you to my web server that says, oh yeah, welcome to Microsoft.com. Oh, by the way, or welcome to Amazon.com. And I may even pull down on my fake web server all the little graphics, and I just copy their page. But we need you to log in. It's been too long. And so we want you to type your old password, and then you can type in your new password. And what I'm doing is I'm stealing their password. So you do not do dynamic IP on your publicly accessible DNS servers. But on the back end, we want to be able to register names to IP addresses and IP addresses to MAC addresses. IP addresses to MAC addresses is done via DHCP, but name to IP address is done by DNS. And we have, 400,000 machines. I don't want to have to go to each and every one of them and statically write it. So they have this thing called dynamic DNS. What dynamic DNS does is it'll allow you to register it. Now, depending upon how you set up dynamic DNS, when I do a query, the DHCP server will register it for you automatically if we're using DHCP. Or I can have clients that when they get the IP address, they will register the information with the DNS server automatically. And when I created that brand new zone, one of the things that we did, if I bring up the properties of the zone, is what type of updates do we allow? Now, this is a Microsoft DNS server. And one of the things that Microsoft DNS servers do is when you're using dynamic DNS, you can specify secure only. So if somebody registers the name, I am going to use the security identifier from that device. You have a domain member, I have a server, it registered the name. That server has a security identifier. I'm going to put that security identifier on the metadata for this particular entry. So if somebody else tries to change that record, their security identifier doesn't match, and so that record is not allowed to be changed. But if I'm having the DHCP server register for it, maybe we're registering names for my Linux machines who are not domain members, I can configure my DHCP server to automatically register it on their behalf. It just means it's going to show up. So if you want to be able to do that, you could say secure only. Now, you could also do secure and non-secure. that says if you have a SID, we will protect that record with the SID. If you're a Linux machine and we don't have a SID and we're not going to have the DHCP server register it for you, we're going to have you register it, or we're going to have the DHCP server register it, but we don't want the DHCP server to own it. Then what will happen is it'll be just up there. It's not listed as secure, doesn't have a SID on it, and anybody can change it. Non-secure is a little bit nervous, a little bit nerve-wracking. But in Microsoft, ooh, must have swallowed a bug. But in Microsoft, if you want to do secure DNS, you have to use Active Directory. It stores it in the Active Directory partition. But we can do it that way. So dynamic DNS is nice because you can update it, but I really recommend that you don't do that except for internal components. And that's where we get into internal versus external DNS. In my internal environment, I can have my domain controllers also be DNS servers. And that's where you get that dynamic updates. And that's where you can get secure dynamic updates. And to avoid a single point of failure, we can replicate this information to other domain controllers. And you have different scopes. You can say replicate it to just these particular servers, replicate it to every domain DNS server in my domain, or I could say replicate it to all domain controllers in the entire forest, so that you would be able to have these records replicated out. Now, here, external, we're probably going to do those static. Internal, we can do that as a combination of static and dynamic, just depends upon what we want. Here's where you run into problems. Let's say that we do website development. And in website development, I have a little web server here that we build up our pre-production stuff just to make sure it works. We also have a copy of our website so that when clients are coming in, they can go to the internal evilhackerempire.com, which also has an employee portal. Maybe it has some other stuff in there that we don't want exposed to the public. But if you try to go to evilhackerempire.com from the outside, you will resolve to this IP address, and that just has the IP addresses for the mail servers, the MX records, as well as the web servers, and so on and so on, and they're hard-coded. So all of a sudden I get an email at my help desk that says, hey, the web server's down. So I fire off my little support console, and I say, hey, www.ehe.com, and it pops up for me. Well, remember, my internal DNS is pointing me to this guy, not to that guy, not to that external IP address. And so now I say it's up for me, and yet I'm not looking at the right server. Not looking at the right server. So another thing that we can do is I can say, all right, well, on this testing machine, I'm going to use this DNS server, not use the internal DNS server, so that I can check to see that external. But we're in a screen subnet, and it's not just one firewall, we have two firewalls. So my request from the internal address of 10.7.9.3 goes through the firewall, and all of a sudden we now have a problem. Because one of the ways that hackers will try and attack you is they will find out what your internal IP address is, or they'll just guess. Chances are it's a 10 dot something. Maybe I'll just go, I'll do a what's called a war games dialer. It's an IP scanner, and you put a starting IP address in, an ending IP address in. Now, we don't want to kick off the IDS IPS, and so we can do them in random order, or we could just go the first one, the second one, the third one, the fourth one. But normally they do it in random order. Also, I'm not going to try and go in and maybe scan what ports are in there. I'm trying to be a little stealthy, so I just want to see if that IP address is live without actually interacting with it much. So I'll send a request to synchronize, and when I get the acknowledgement, I'll write it down, and then I'll move to the next one. And then your server will eventually time out, but I haven't triggered that IDS IPS. So we really want to be careful about what addresses are allowed in and allowed out. Now, another way that they attack is once I figured out what your IP addressing is, I will put as a source address one of your internal addresses. Oh, we're 10.7.9.15. Oh, and by the way, that source address, I'm going to send it to this guy right here, and I want this guy right here to do 10,000 requests to synchronize over and over. Oh, actually, no, I'm doing this wrong. So that is an internal address. We'll say that it's the IP address of this particular server here. So even though it comes in this way and it sends it to this particular, oh, no. We're going to put in the source address of this. The destination address would be this guy right here. So I'm telling it, hey, by the way, we want you to send 10,000 requests to synchronize to I'm doing a request to synchronize. This is a source address, which is this guy right here. I'm sending 10,000 of these, and so this server will do the acknowledgement and request to synchronize 10,000 of them using this as the target because I lied about what the IP address is. Here's the thing, though. When you're coming in from the internet, this is a private IP address right here. They're set aside. It's RFC 1918, I think that's the one with private IP addresses. And it just says, these are addresses that don't work on the internet. These are used internally. You have to have public IP addresses to use that. And if the source address coming in through this firewall, oh, the source is right here, it's coming from the outside and yet it's trying to pop through, somebody is spoofing that address and it'll throw it away, throw it away, throw it away, throw it away. Okay. That sounds pretty handy. So if you give me a bogus source address for an internal, and instead of me attacking myself, my firewall catches it and throws it away. Sounds great. Here's the problem, though. So I have my management console in here again. So here's my management console. I want to be able to see this server, and I want to be able to get that web page back. My source address is going to be a private IP address. It makes it through the firewall, but then when it has a destination IP address of an internal address, because originally that was my source, the firewall is going to say, dude, that's an invalid address. We have somebody spoofing the address. We're going to ignore it. And so now I can't communicate. So if you're doing screen subnets, you also have to be careful with your firewall to make sure that if you are going to probe the public stuff, you either go out through the internet and come in that way using a public IP address, or if you're going to have access control list that says, oh yeah, this is a management console, allow it through, you would have to modify this access control list that says specifically either this IP address, or maybe I have an admin subnet like 10.107. I could say anybody coming from 10.107, allow it to traverse bidirectionally the firewall. And this is a very, very, very common problem. You either pointed to the wrong web server, or when you try to point to the right web server, the firewall says, hey, you're doing a loop-de-loop through the firewall. Not allowed. Not going to be allowed. So, and that's the big thing there. All right, now, let's talk about how DNS works. And by the way, all of this stuff right here, it's not in your book. When Todd wrote the book, this was before they changed some of the exam objectives because they did the beta and now they're modifying and modifying and modifying it. And one of the things that CompTIA is saying, we need to know more about how DNS operates so that we can test you on it. It's also important information to know. So how does DNS work? Well, what you're going to do is you're going to have root servers. These root servers are who I asked. Let me actually illustrate this. So here I am on my particular machine. So that is, Doug server 23 or Doug client 23.evilhackerempire.com, and I want to go to server 5.microsoft.com. In fact, I'm going to go even deeper than that. I'm going to say that this is going to be, let me get my head out of the way. I'm trying to go to srv5.sales.microsoft.com. Now, my particular machine, first thing it's going to do is it's going to say, hey, do I know where srv5.sales.microsoft.com is? Have I resolved it recently? And is it still in memory? Do I have it in cache? Questions and answers. What setting in DNS determines how long you will work off of what's in memory as opposed to doing another query on DNS? What setting on the individual records defines how long we'll remember it? It's TTL. And that is set by the DNS server that is authoritative for that zone. Authoritative means that if you send me a query and it says, oh, I want to go to Evil Hacker Empire, I have the zone file for it. And so I supposedly know everything Evil Hacker Empire. And if you do a query and I can't find the record, I'm just going to authoritatively say, no, that's not an available record in there. So I go in and I say, all right, I want to go to server5.sales.microsoft.com. I do not have it in my DNS cache, so I'm going to send it to my DNS server. This is my DNS server. I'm going to say, hey, DNS server, I want you to do a lookup for me. And in fact, I want you to do what is called a recursive lookup. Recursive. And we have a slide on recursive. I want you to do a recursive lookup. Now, what a recursive lookup is it says, look, I don't want to see every bounce along the way. I want you to resolve it and you can give me the IP address. I mean, you can give me the other stuff too, but give it to me in one big package. I want you to look it up for me. And then the server curses me because now it has to do all the work. So that's how you remember recursive. You're asking somebody else to do it for you. Now, the first thing it's going to do, because it is a DNS server, is it's going to see if it is authoritative for that. So it'll say, do I have a zone file for Microsoft.com? And on your DNS server, you can put a zone file for anybody you want. Let's say you get approval for it, follow your change control process. But let's say our company doesn't want people looking at Facebook, period. Not allowed to do Facebook in any way, shape, or form inside the company. So what you do is you make a zone file on your DNS server called Facebook.com, and you don't put any records on it. So when they try to resolve anything for Facebook.com, it hits my DNS server and it says, oh, I'm authoritative for Facebook.com. I have no records, so you can't get to Facebook. Now, does that take Facebook out? No, because nobody is pointing to this DNS server to try and resolve Facebook.com. The only reason I'm going to this DNS server is because I was told by DHCP, hey, send it to your DNS server. So let's say that I do not have a zone for Microsoft.com. And by the way, that could violate federal law because you're redirecting stuff and it could be considered hacking. That's why you get written approval and you print it and hang on to it in case they want to try and throw you under the bus for violation of the U.S. Patriot Act, and you don't want to end up having to deal with it. So now I don't have the zone. I'm not authoritative for it. So who do I ask? If it was a Wind server, if I don't have the file or I don't have the record, I don't ask anybody. DNS is different. It is a distributed name service. So here's the interesting thing. At the end of every URL, at the very end of every name in DNS, there is a dot at the very end. That is called the root domain. That is known as the dot domain. It sits all the way at the top. Now, these root domain servers, if I go into the properties of the server here, you'll notice that we have what is called root hints. These are all of the dot servers. There's 13 of them. Now, they can give you IPv6 addresses. You can also get IPv4 addresses. There are more than 13 servers, but this points to 13 load balancers that have load balancers behind them that have load balancers behind them, and there are thousands and thousands and thousands of behind-the-scenes servers, but we only have 13 IP addresses. A few years back, they had an attack that took out 11 of the 13 IP addresses, trying to nuke the DNS service. And guess what happened? Nobody noticed. Because even though I only had 2 public IP addresses, that has such a heavy back end on it that nobody noticed and everything worked fine. So even though there's 13, it's not just 13 servers. But that's where we go. So now I'm not authoritative for it, and what we're going to do is we're going to do a series of iterative queries. And iterations means you get closer and closer and closer, but I do the various hopping. So I did a recursive that says, find it for me and don't talk to me until you get it back. So then I say, well, Microsoft.com, I'm not authoritative for it. I'm going to go to the unnamed root and I'll say, hey, I'm looking for server5.sales.microsoft.com. Well, the unnamed root has no idea where server 25 is, has no idea where sales is, has no idea where Microsoft is. The only thing that it knows about is .com. It has a list that's called the top level domain. It has a list of the .com server. It has the .mil server, the .gov server, the .uk, .us, .jp, .xxx, everything. Everything is on these top level domains. And so it'll say, here is the IP address of the server that is responsible for .com. So then I go to the .com server and I will say, hey, I'm looking for server5.sales.microsoft.com. Well, the .com server doesn't know server 5, doesn't know sales, but when Microsoft decided to go on the internet, they had to register the name Microsoft.com. And as part of that registration, we had to say who the name servers were that were responsible for it. You have to have at least two, primary and a secondary. That is how Microsoft.com gets registered in the .com. It'll just say, oh, these are the IP addresses for the name servers. Questions and answers. What type of record identifies who is authoritative for a DNS domain name? Chat it in. Is that an SRV, an SPF, a TXT, an NS, an SOA? Which one is going to identify where my name servers are? Chat it in, chat it in, chat it in. And a lot of people are saying SOA records. Nope, nope. But dog, you showed me on the SOA record that it had a list of all the name servers. So if I go in here and I bring up the SOA record, it says, oh, look, here's the name servers. Isn't that an SOA record? Microsoft combined them, but they're not. If you go in the dialog box, the way that you identify name servers is you have an NS record. So these NS records is what is stored up in the .com. It says you have this IP address or this IP address, and that is what is returned to my DNS server. It says I'm not authoritative for Microsoft.com, but here's the name servers that are. So then it gives me the IP address of the Microsoft.com name server, microsft.com. So I send that query over to Microsoft.com saying, hey, I'm looking for server5.sales.microsoft.com. Can you help me out? And if Microsoft stores everything in the Microsoft.com zone, then it would go into the zone file, dig through it, find it, and then say, hey, here's the IP address. However, it is authoritative for the name, but we're doing what is called a delegated subdomain. Let's say, for example, that for sales, Microsoft doesn't want to host it. They don't want to host the records for it. Instead, this is going to be hosted by GoDaddy. So it could say, oh, for that particular name, we have a delegated subdomain, and the machine that you need to go to is server15.godaddy.com. So then my DNS server goes, oh, great, unnamed root. Hey, I'm looking for server15.godaddy.com. Oh, I'm looking for the name server for GoDaddy. Here's the GoDaddy server. That GoDaddy server happens to have a delegated subdomain for sales.microsoft.com. So now I send the query there and I say, hey, I'm looking for server5.sales.microsoft.com. Oh, I have sales.microsoft.com. You want server 25 or server 5? Here's the IP address. Now, each of these resolutions, each time I'm pulling this stuff in, all the Microsoft.com stuff, all the GoDaddy stuff, that is being stored in the cache on the DNS server based on its time to live. Then, because now the query is complete and I got an IP address, I will send that as the answer to the recursive query to the client. They will then also store it inside for their time to live. And then, until those records expire, I won't ask DNS anymore. I will just say, oh, I have it resolved, I have it resolved, I have it resolved, until the TTL expires. So you can have somebody who is authoritative for that particular zone, or you can have delegated subdomains. You can even have delegated subdomains like northeast.sales. You can delegate those, and they don't even have to be supported by your name servers. For example, evilhackerempire.com. I don't run the DNS for it. I run the internal DNS for it, but I don't run the external DNS with public IP addresses. I let GoDaddy do it. So when they go in, I've registered DNS for Evil Hacker Empire. They will say, who is the name servers? The name servers that come back will say, oh, it is for GoDaddy. Here's a fully qualified domain name for the GoDaddy servers. Then I go to the GoDaddy servers and get those IP addresses, and it's just a continuous process. But here's the cool part. Let's say that I change the IP address of server 5. I don't have to go to all the DNS servers on the entire planet and change that IP address. Because it is distributed, the only place I have to change it is on this guy right here. That's all I have to do. And it makes it so that I have a place to appeal if the server, which is authoritative, doesn't bring it in. Let me show you this. If I go back into that cool little app called DNS Lookup, so we'll do a CLS, and I'll say DNS Lookup, and I say www.microsft.com, it gives me the answer, but you'll also notice it says it's non-authoritative. Does that mean I talk to Joe Bob's DNS server to pull it in? No. What I'm saying is that the server that I'm talking to, which is this DNS server, doesn't have a zone file for Microsoft.com. It's clear over here. So when it gives a response back to my client, it is going to tell me, oh, by the way, I'm not authoritative for it. I asked another server, and these are the responses. It actually has a bunch of CNAME records and all this other stuff, and here's all the IP addresses. In this case, it's giving me the IPv6 address and the IPv4 address of the ultimate destination. So that's what we have. All right, so let's go ahead and take a look at this with the official slide. So the root DNS server, it's up at the top. It has the root zone. It has all of the addresses for all the name servers for .com, .mil, .gov, .jp, .whatever. And there's 13 of them, but it's a front end to a load balancer. So with DNS Resolution, I will send it to the DNS server, and that DNS server will forward it to the root only in a particular instance. When will a DNS server not forward a DNS query to the root? Chat it in. When will the DNS server say, oh, I got this, and not forward it off to the .domain? What circumstances? Chat it in. Why would I not ask? Because I'm authoritative. Remember when I said you make a zone for Facebook and now all of a sudden nobody can get to Facebook? Exactly. It'd come back and it'd say, oh yeah, it's authoritative. Well, you know what? Facebook is not in my company. So if I'm saying, why can't we go to Facebook, and I type in, hey, I want to go to facebook.com, and it comes back and it just says, here's the address, but it doesn't say it's not authoritative, that means that particular DNS server has a zone file. And you can change DNS servers. Check this out. I can say server 8.8.8.8, which goes to Google's DNS server, and I say www.google.com. Let's see what happens. Oh, it's not authoritative. So the DNS server of 8.8.8 doesn't actually host the DNS record for www.google.com. It's got to go somewhere else to try and find it. So it looked it up for me. I did a recursive query, and it says, okay, here's the IP address. So it gives me a non-authoritative answer. These are essentially just shell DNS servers, and they're not really hosting any domains, but they will respond to queries, and then they can harvest those logs for what people are searching for and then monetize it. That's what they can do. But you can use this if you're saying maybe my internal DNS server is not working. I could test it from the outside. Also, by testing this from the outside, I could say, is it resolving to the internal DNS or the internal resource, like that internal website, or is it giving me the public IP address so that I know it's going to that public IP address? That's what we have. So it just goes through and it says, okay, bounce back and forth, back and forth, back and forth, and I will tell you who the authoritative name server happens to be. Now remember, we have a hierarchy. We have the top level domain, which is .com, .org, .net, and at the root, we have the root. Questions and answers. How many root IPv4 addresses are there? Chat it in. In other words, how many root DNS servers supposedly are there? Or how many root load balancers are there? How many do we have? How many do they have? Yeah, there's 13 of them. And then you have secondaries, and then you have third-level domains. We got that one. We already know how caching works. It's all going to be based on the TTL. Oh, an important note here. Let me show you this. So if I do all these queries back and forth, it is all being cached based on the TTL of the DNS server. On my machine, it's also caching it based on the TTL on my machine. And I put in the wrong IP address when I was configuring DNS. I type it in. Oh, no, that's the wrong IP address. So I go to my DNS server, or the DNS server responsible for that, and I change the IP address to the right value. And then, to make sure that I'm not using the old value, I do an ipconfig flush DNS, which kills this DNS query. And yet, when the result comes back, it's still the old answer. Even though I updated the record. I gave it a really short TTL, and yet it's still the same answer. Why would that be? So I find it's wrong. I quickly change it. Maybe I have a script, takes like a millisecond, changes it. I flush my DNS cache, and yet I'm getting the same answer. Why would that be? Why would that be? Why would that be? It's because I'm still asking the server. And the server, it still has it in its cache. I didn't flush it when I did a flush DNS. I flushed it on my machine, but I didn't flush it on the server. And so it just pulls it out of the cache and gives me the exact same information. So you really got to be careful with TTLs. One of the things that, let's say that you want Microsoft to host your website, or you want Microsoft to host your DNS. What they're going to do is they're going to have you say, all right, well, it's not a new domain. You already have somebody else hosting it. Prove that you own it. And what we want you to do is we want you to put a special number, and here's the weird number. We're going to have you put that in a text file on your DNS record. That is how they prove that you actually own it. And the problem with that is if you have a 60-minute TTL on there and you fat finger the code, you transpose two of the numbers, when it verifies, it's going to fail because it says it didn't match. So then I fix it, change it on my DNS server, and I say check it again, and it says fail. Why did it fail? Because it's using that cached record. So when you're doing verify, you want to have a very short TTL until it's verified. In case you screw something up, you don't have to wait an hour to try and fix it. Or, you set the TTL for like 30 days. I got to wait a month to bring up our provider. You don't want to do that, so bring it down. Dan's asking about recursive and iterative. We'll talk. We actually have slides on it. I've mentioned it before. Recursive, my server curses me because I tell it to just respond with an answer. Iterative, it just goes and bounces back and forth. And through several iterations of queries, it gets closer and closer to the answer that I'm looking for. So that's what that is. So just be careful with caching because it's not only cached on the client, it's also cached on the DNS server. The next one is zone transfers. We talked about this. You have a zone on one server and you want to have a read-only copy on a secondary server. We will just copy it over. Now they say, oh, we're not going to allow you to do zone transfers outside the root zone. That means, oh, I can't do zone transfers and pull down the dot domain. Big surprise. They'll replicate amongst each other, but if I try and do, oh, I want to be a secondary root server, they're going to go, no, and you can't do it. So zone transfers. DNS zones, it just means that I'm authoritative for that namespace. It doesn't actually have to be hosted by a server that's owned by the company. Like I said, Evil Hacker Empire, their DNS is hosted by GoDaddy, for example. Before that wasn't a good idea because GoDaddy, if you called them up and said, yeah, I'm the administrator for Evil Hacker Empire, my name is Susan, and your records are wrong, I need you to change it. This is the new IP address. And GoDaddy would say, cool. This happened for years. Years where you just give them a call and they'll change the record for you. Oh, you need it updated immediately. They would do that. And then all of a sudden somebody found out about it and started hacking and people started freaking and then GoDaddy goes, my bad. So for a while people wouldn't trust GoDaddy. I love GoDaddy personally, but they had some problems kind of growing. So remember, the zone file doesn't have to be hosted by your machine. I went to Google's DNS server and Google's DNS server responded with a non-authoritative answer. because they're all delegated to other DNS servers. That's what we have right there. All right, forward lookup, reverse lookup. Forward lookup, you're matching a name to an IP address using an A record, CNAME record, all that. Reverse lookup, you're matching an IP address to a name. So you already know the name and the IP address, you just want to verify it. So then you do a reverse, and that's going to use a PTR record. PTR record. All right, recursive and iterative. Recursive, I tell you, find the answer. You curse me, because now you're going to have to bounce up to the unnamed root and all that, and then give me the answer. That's typically the type of request I'd send to my DNS server, especially since it's non-authoritative. Now, if I do an iterative query myself, that is where I have to do it. So remember the difference. Recursive, I'm telling somebody else, and they curse me because they look it up for me. Iterative, I have to look it up. So, oh, you tell me unnamed root. Okay, so I have to go to unnamed root. Oh, you're telling me .com. I have to go to .com. And that's the type of queries that DNS servers typically do, bouncing around trying to resolve. It's a series of iterative queries, but the clients typically request a recursive query. That's the big difference there. Now, they also talk about advantages of recursive and disadvantages. Recursive is faster because that server who's looking it up for me, they can cache it for me. So I don't have to do individual lookups. If I decide that I want to do a iterative series instead of doing recursive, then I would have to do it, but we don't have to worry about the cache being poisoned, because there's an attack called cache poisoning where I will give you a response faster than the real DNS server, and I say, I'm evilhackerempire.com, I'm Microsoft.com, and as long as you believe it, that's what you're going to give the clients, and away they go. So having another server do it for you, that proxy server, it's a DNS server, but it's acting as a proxy for you. You have to make sure that that doesn't get corrupted, doesn't get penetrated, because if I own your DNS, I own your entire company. So that is DNS. They show you how the lookup goes. It just bounces around. We already talked about that. They also talk about iterative, which means I do it, so that's iterative. And it essentially is acting as a proxy server. Now, remember, when we're going through DNS, I will send a recursive query to my DNS server. And here it shows I'm sending this stuff directly, but that's not what happens. So I send it to my DNS server, and then my DNS server does a series of iterative queries. Because remember, my DNS server is not authoritative for the zone I'm trying to find. So what will happen is it goes to that unnamed root, which is the .domain. Now, the .domain doesn't know where anything is except for the top level domain, which would be like at the .com server. And this is where you would be asking for the name servers for wherever you're going to. Now, this is going to Google. It's going to say, hey, where are the Google name servers? And then that's where Google has registered with ICANN or some registrar, and that has populated the .com server with the two name server records specifically for Google. And that's why if I just say, oh, I'm Google.com, and I advertise everything as Google.com, nobody can find me, because the way they find you is they query the .com server. So unless it's registered, nobody on the outside is going to be able to find it. But you can have internal DNS. You can even have internal DNS that's hosted by somebody else, or you could have it so that you tell the .com server, oh, by the way, these are the people who are registering it for you. So, and this is what we're going to start off with over on page 160, talking about third-party and cloud-hosted DNS. Now, as far as cloud-hosted DNS goes, my favorite, because that's the one I know, is Azure. And Azure is not going to register the domain for you. So you have to have the name already, and usually it'd be like, GoDaddy or somebody. And then once you decide that you want Azure to host your DNS, you have to either update the .com, or you tell whoever your registrar is that you are going to delegate it to a different name server. So let's go ahead and show you. So up here, I'm going to go into DNS zones. And these could be private zones, these could be public zones. It just depends upon what it is that you're going for. And I'm going to create a zone. And we're going to put in Evil Hacker Empire. So we'll hit create, and we'll give it a minute. We'll give it a minute. There we go. All right, now let me get my head out of the way. So you have to tell it where you want to place it, and this is just to store the information. We'll put it over in east, and then we'll give it a name, and we're going to call this one evilhackerempire.com. And then one of the other things that they do is they allow you to put meta tags on it. Meta tag is just data about data. And what this does is it helps with billing, and it helps with trying to find out, if a particular person did a whole bunch of stuff, I could do a search off of these tags and find out what particular resources was created or used by this particular administrator. So it just gives you the ability to go in and do a little bit more identification inside of there. So this is cloud computing. Now, Microsoft's DNS servers are astonishing. They have a service level agreement, which means they will always, or this is how much they'll do. It's a service level agreement of 100% availability. So that if you try and get a hold of a Microsoft DNS server, you will find a Microsoft DNS server. They use something, well, it's called Traffic Manager, which is a DNS-based load balancer that will be able to find out the closest DNS server to wherever you happen to be, because IP addresses are geographic, and it'll send you to the nearest Microsoft DNS server. Also, one of the big challenges, have you guys ever had to play around with DNS and you want to change from one registrar, you don't like GoDaddy anymore, you want to go over to, I don't know, VeriSign or something like that. You have a problem with the TTL. Also, if you add a record, it takes a while for it to propagate. Be able to go to all the other copies of the DNS server that particular provider has. Azure, when you go in and you put in a domain, and you prove to Azure that you own it, so this would be a public domain, when you make a change, the change happens literally in seconds. It goes to all the DNS servers in the entire world that's ran by Microsoft within just a few moments, which is wildly different. I've seen where it takes 48 hours, 72 hours for these records to propagate, and that is a big hassle because, oh no, we've changed. And that's why if you're going to swap out providers, you want to leave your old stuff up for a while, change the new stuff, monitor the traffic, and as soon as it starts going to the new stuff, then you can shut down the old stuff. So it can be a bit of a hassle here. So let's go ahead and take a look at this. And this is evilhackerempire.com, and you notice that it has a couple of records. It has a name server record, and this is very important because these are all of the name servers that Microsoft is using to host this particular domain. Now, I haven't proven to Microsoft yet that it's actually owned by me. So if I go in and I copy this guy right here, I go in and let me back this up a little bit. I go in and I copy these name servers, or I can just grab them up here. They actually have a little thing that lets you copy it. I would be able to use that to try and say, hey, who has, evilhackerempire.com or whatever. And because I haven't proven to Microsoft that I own it, they're not going to advertise it. But once I go in and verify it, then we're good to go. Now, there's a way that you can do this. You can go in and you have all the name servers, and what I'm going to do is I am going to go to my actual registrar, which is GoDaddy. And inside of GoDaddy, I have a whole bunch of records and all this other stuff. And notice we have the TTL. Now, one of the other things that I've had to do is I've had to prove to Microsoft that I've owned Azure, or that I've owned Evil Hacker Empire before, because that's my internal domain inside my environment, and I actually owned the name. And so when I was doing things like Traffic Manager, where I was trying to prove this, or if I was trying to hook the Active Directory on premises with Azure Active Directory, and we wanted it to replicate, they want to make sure that I'm not just spoofing somebody's name. And so what they did is they said, all right, you want to set up this Azure Active Directory Connect to be able to replicate the stuff. We need you to go to your DNS server and put this record in right here. It's a text record because, it's like SPF records or DKIM records. They don't have a special one for verifying Microsoft. They said, hey, we're going to do text records. And then they will give you a value, and by default, the TTL on it is going to be 10 minutes. So actually, I think by default it's an hour. And so if you fat finger this code, you know, I transpose two of these numbers, or here I did another one that has a whole bunch of characters in it, what's going to happen is that if I put it in there, it tries to verify it, I messed up the number, it'll say, sorry, you can't do that, but the TTL is set to an hour, which means I have to wait an hour before I can try again. So you can drop this TTL, and I think the minimum that Microsoft will allow you to put in for verification is 10 minutes. So you have to do 10 minutes. But if you mess it up, hey, you got 10 minutes to fix it, or you got it however long you want, but you don't want to re-verify it for 10 minutes. Now, you'll notice that it also has the name servers. And what I can do is I can go in and I can change the name server. So for example, here is, well, actually I don't have it here, but what I can do is I can go down, these are the default name servers, and I would get all 4 of these addresses. Now, wait a minute, this is .net, this is .org, this is .info. It doesn't matter, they delegate the domain back and forth. It gives you massive amounts of redundancy. That's why they have that 100% service level agreement. So I can go in here and I would say I want to change the name servers, and then instead of using the regular name servers, I would enter my own name servers and I just put them in. Now they require at a minimum you have 2. I have 4. So I would add all 4 name servers in here, then I would wait for it to propagate because it's going to be up inside of GoDaddy. Then here's the cool part. When somebody comes up doing this iterative query, it will say, oh, by the way, this is hosted by GoDaddy. So I would have to go to GoDaddy's authoritative name server. And here's the cool part. By default, it goes to GoDaddy's name server. You go up there, they're the ones that have it, boom, there we go. But when I swap out that record, it is actually going to modify the .com so that now it'll say it is Azure, once I've proven to Microsoft that I actually own it. And so you would go in, you'd point it to your name servers. Microsoft would be able to see that and say, oh, okay, it's going directly to me. So when I go up to the unnamed root, I go to .com, it's not going to give me the name servers for GoDaddy. It's going to give me the name servers for those new addresses, which is in Azure. So, and there's a lot of capabilities that you can have. For example, let's say that we're in a private environment. So I have my private virtual network. I have all these servers and things in here. Now, in the cloud computing environment, they have built-in DNSs. But what it does is it just dynamically registers anything that you put inside of your virtual network. It's not registered out on the internet. You don't even have any public access. But I can set up a DNS zone, and I can tell that DNS zone expose that DNS stuff as a private endpoint inside that virtual network. And what a private endpoint means is it essentially takes a service, gives it a pretend network adapter, and plugs it into your virtual network. So it is local, so we can localize the traffic. Then, as I'm trying to resolve resources, maybe I have resources that are on premises. I could put those records in there as well. I could go in and have it so now I have a couple of virtual networks. Maybe we have a private VPN tunnel where we've done peering and they have resources in there as well. Maybe I have it go through my on-premises network, and over here we have this going through the on-premises network, but we want this side to be able to resolve this way and this side to be able to resolve this way, and down here and over here. And again, you just add all of these components. So depending upon who the third party is, you're going to have a variety of options and experiences that are available for you. But remember, when you type in, evilhackerempire.com, we have to match that to an IP address, and we use DNS. And if it's publicly available, they can query it out. But you could also use it as a private domain, call it whatever you like, and then it would work for you in that. And you can even host multiple domains inside of Azure. And the private domains, you don't have to verify anything. You don't have to copy who the name server is, because internally you just point it at these internal name servers, Azure DNS, and it'll take care of it for you. Now, you could also set up a virtual machine and have a regular old DNS server. But in fact, in Marketplace, if I go up here and I type DNS, they have a variety of DNS servers already set up using different flavors of DNS. So if you want to go in and let me show you. So if you go in and you type DNS, it'll show you up in Marketplace where they already have virtual machines. It's already configured, And when you go in and buy it, you just buy it for however long you use it. And then if you don't need it anymore, you get rid of it and you're not locked into a bunch of hardware. So it makes it pretty handy. So DNS, very, very, very important because that's how we find out where we can authenticate. That's where we find the Kerberos servers, the LDAP servers, global catalog servers. This is how we can locate web resources. Everything revolves around DNS. And if I can get your DNS, I have your company. So you want it to be nice and secure. Now, another thing that we have is we talked about how we would use a global catalog server to try and authenticate using Kerberos because we have the SRV records that will say, hey, this is where Kerberos is. Now, Kerberos is a pretty powerful protocol. What it does is it does mutual authentication. It also goes in and has anti-replay attack stuff. So back in the day, you could just sample a bunch of packets, snapple, grab them all and sniff them up. And then you retransmit them. And then you could use that to piggyback on somebody else's authentication. Well, Kerberos doesn't allow that because it has a timestamp. And you only have a 5-minute window. So if I send something out that's more than 5 minutes old, then Kerberos is going to say, hey, this is a replay attack, and it's going to toss it away. Okay, so I'm protected. Why am I worried? Well, these computers, they have their own internal clock. And these internal clocks can be influenced by environmental issues. It's too warm or whatever. It makes the clock run faster. There's spikes. It's just a poorly designed clock. Who knows? And so you're going to go through and you're going to have clock drift. So what you want to do is you want to have a single time source. Now, when you're looking at, again, Microsoft Active Directory, they synchronize their time. You have the first domain controller that you've built inside of your forest. That's going to have a role on it. It's called a flexible single master operations role. And that role is a PDC emulator, primary domain controller emulator. Back when Active Directory, you had one read-write copy on the PDC and everybody else was a read-only copy on the backup domain controllers. But now it's just everybody's multiple master, no problem. However, they still have that role in there because that is the master time clock for the entire domain. So when these domain controllers synchronize their clocks, what they do is they talk to the machine designated as a PDC emulator, and they set their clock to whatever that clock happens to be. Then as machines authenticate, because you have machine accounts in the domain, when they authenticate, they're going to reset their clock with the domain controller. So in theory, the one that they authenticate with. So in theory, they're all going to have the same clock, and we're not going to worry about that 5-minute clock drift. However, that requires that all the domain controllers have access to that primary domain controller emulator, the PDC emulator. And a lot of times, because that's the first machine, it's often the bowels of the data center in corporate. And if you happen to be in branch offices where we have another domain controller out there, they may not have direct access to that. And if they can't gain direct access to the PDC emulator, they just go, oh, well, I'll just go ahead and use my own clock. But after a while, their clock drift gets more than 5 minutes and it quits replicating. So having an accurate synchronized clock is very, 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 very important. So how do you do that? Well, you have time.microsoft.com, but the official clock is going to be with the National Institute of Standards and Technology, also known as NIST. Now, in your book on page 160, at the bottom, they have a website, which is this website, which is tf.nist.gov/tf-cgi/servers-cgi. And what it does is it has a list of all the name servers that it uses. These are the name servers. It gives you the IP address, gives you a fully qualified domain name, tells you where the location is, all of that stuff that will set your clocks for you. And if you do not have access to the PDC emulator for your other domain controllers or whatever thing you need to synchronize your time with, what you can do is make sure that the side you can't reach is synchronizing with a time standard, which would be NIST or time.microsoft.com. And you would make sure that the guys that can't reach the PDC emulator, they synchronize with the same clock source. So now we're going to be resetting our time And in the book, he says, oh yeah, a lot of times they'll go in and they'll reset it every, every minute or every 30 seconds or every 30 minutes or whatever. It depends on the operating system. A lot of times these operating systems does it once a day. That's about it. I mean, how bad is your clock that it's drifting that far? But if you're dealing with something that needs, microsecond accuracy or something like that, you're doing satellite communication, you're trying to synchronize your GPS, well, you're going to want to have it very, very, very accurate. And those types of devices will go in and they will reset their time continuously. Now, one of the problems with NTP, and like I said, you just go in and you tell it. Because if you go into your clock, let me show you this real quick. I'm going to click on here, CLOCK. And you would be able to go in and set the time automatically. Now, I have it set with a group policy that says, hey, this is where you set your clocks. Here we go. You don't do it yourself. And so this is turned off. Now, I can say set the time zone, but what I'm doing is I'm saying I'm in Arizona because, I'm in Arizona. Then I don't have to worry about daylight savings time or anything like that. But the way that you go through and make changes is going to vary depending upon the operating system. This is Windows Server 2016. So it has a very specific thing. Now, another interesting thing about NIST and their time servers is, we'll talk about this when we're hacking, but when we're talking about hacking, is that I can query it and say, hey, give me a list of the last 600 people that requested it. And it'll go, here you go. Now, the problem with that is I can use that as a distributed denial of service attack. Because if there's a website that I want to take out, what I will do is I will spoof the source address. It has to be something that's reachable by NIST. I'll spoof the source address and I'll say, hey, give me that transfer, give me that transfer, give me that transfer. And I can have a whole bunch of machines that's scattered out. Or in this case, I could just have one machine that's doing like 10,000 things. And then because I've identified the source address as that target, NIST used to just stream tons and tons and tons of this stuff and overwhelm the buffer because the last 600 people times 10,000 times per second, that is a lot of information. So, and when we get into some of the things that the hackers do, we'll show you how that works. Now, what they've done to try and prevent that is they say, hey, we're not going to do all these massive transfers like we used to. But, while it was there, the hackers did go through and take advantage of it. So, being able to have a nice synchronized clock is very, very, very important. All right, on the bottom of page 160, we have a proxy server. Let me get to the right button here. There we go. We have a proxy server. And what a proxy server does is it acts on your behalf. So, for example, I want to be able to go out and go to a website. So I want to go to Evil Hacker Empire. I want to go to goathop.com. It sounds like a safe one. You got a picture of a goat that's hopping around. Really, really cool. And so I send it to the proxy server. And this proxy server can have all sorts of jobs. It could act as a content filter. You could put a list of allowed websites. You could also have it do caching for you, where I could have it cache like shipping information, billing information, credit information. I don't know if I wanted to do that. But so that when I'm filling out a form, the proxy server will automatically have the stuff already filled out because it recognizes what the fields are. And then I just have to fill in the last little bit and then boom, away it goes. So they can do a lot of stuff. But one of the big things about proxy servers, it goes in and it pulls down goathop.com. And then I send it to you, and it's going to store it in here. Now, we don't have a TTL on this. Instead, what will happen is when somebody else goes in and queries it, it's going to do a quick check to see if anything has changed. And since it hasn't changed, it'll take its cache copy and deliver it to the second machine. So I can have 500 people going to goathop.com. The proxy server pulls it down once, and then everybody else, the 499 other folks, they get it really, really quick because they're pulling it off of the proxy server. Now that would be like a web proxy server. That's a web cache. They have these over on page 161. You also have a caching proxy server so that I can keep the stuff that's local to us, and and the web proxy server can also fill out the billing information and all that stuff that we've talked about. And it's to act as me. Now, there's other types of proxies. This is an official proxy server. You'll see it with web servers. But you also have other types of proxies. For example, network address translation. that is going to convert from a private IP address to a public IP address. That's an IP address proxy. That's what we have. So anything that acts on your behalf is technically a proxy, but they may call it something else. For example, IP helper, that's a DHCP proxy. They call it a DHCP relay agent, but it's a proxy. I'm saying, okay, let me encapsulate it, send it over here, send it back to me, and then it broadcast it. So that's what we can do, but it doesn't cache anything. It doesn't do anything like that. A couple other servers that we need to be familiar with. Now, these are in the exam, but they're not necessarily in the book. We have a TFTP server. They have a little mention for this. When we get into protocols, you'll see this. But what a TFTP server is it uses user datagram protocol, UDP, so we don't have to do the three-way handshake. We don't have to do all that fancy stuff, sort of like how DHCP works. Hey, here it is, and if it didn't work, yeah, you're going to have to ask for it again. Same thing here with TFTP. But what we can do is we use this a lot to store our configurations. So if I have switch configurations, router configurations, I could take that running configuration, I can save it, it'll put it into a little file, and then I can copy it up to a TFTP server, and it just stores it there for us. So you could also use these TFTPs for doing things like Windows Deployment Server, WDS. That's where I can have images. It's sort of shades of boot P. I can have images of operating systems, and then when I pull it down, I'm using TFTP to be able to pull it down. It's actually, well, it depends on how you have it set up. But I pull it down, put that image on my particular machine, and then it reboots, and now it's a whole brand new operating system. The big difference between that and boot P is that the operating system just isn't stored in memory. I actually have the stuff on the hard drive, and those images are just pictures of the hard drive that you have right in there. Usually when you do this, you would have to set your permissions. Some TFTP servers will integrate with a identity provider like Active Directory, or you can use a Kerberos MV5 realm. It just depends upon what you want. But most of them are just going to filter out who can use it based upon IP address. And it'll say, well, if you're from this IP address, you can write to it. But most of the devices, we're going to say, oh, we're going to be able to just read from it so that I can copy the stuff down. So that's what we have. Now, this next one we've already seen, which is a load balancer, but they decided to move this around a little bit. However, because we've already talked about it, here is our load balancer. Let's go ahead and put an icon on there. That's our load balancer. Now, this is going to have a virtual IP address, and then it'll have a dedicated IP address for us to manage it. These are all going to have dedicated IP addresses, but as a request comes in, it will send it to the one that's least busy. And remember, we have health probes and all that other stuff on there. All right, questions and answers. We've talked about this before quite extensively. What am I going to put in GoDaddy.com to be able to go to the Evil Hacker Empire website? So would I put in the dedicated IP address? Would I put in the dedicated IP address of these servers, the dedicated IP address of these servers, the virtual IP address? What do I put into GoDaddy to get people to come in and use my load balancing solution? Go ahead and chat it in. So dedicated IP address to the servers, dedicated IP address to load balancers, or virtual IP address to the load balancer. Yes. Virtual IP address. And we're going to see virtual IP addresses a lot. You know, it's network address translation. We could do that as well. These could have internal IP addresses, but that external one, the virtual IP, that's going to be a public address if we're making this available publicly. So, like I said, we've already spent a lot of time on this, but this is what we have. Now, this one is pretty cool. This is going to be good for device recognition. Here we have encryption and we have content filtering. Now, I can do encryption. I could set encryption on every server and have it do its own IPsec encryption, this and that and the other. And I can do a 4096 key, strong security. However, that type of encryption is very, very, very processor intensive. And if I have a whole bunch of people doing this, this poor little server may get buried. You know, I just want to be a web server. And yet it has to deal with all these terminations of your SSL connection or your IPsec connection. It just depends. So I can offload that to these particular encryption devices. And on these encryption devices, it will terminate here. So the request comes in, we have the tunnel comes up, and it terminates there. This will be able to peel it open, figure out where it's supposed to go, and then forward it on its way unencrypted. And a lot of times when you're dealing with encryption, because of the security and the hashing and all this other good stuff, it's hard to get encryption sometimes to go through network address translation. And so we can have it terminate at that point before network address translation. Then I can send it into the network unencrypted. Or if I'm a little nervous about that, what some of these encryption devices would do is I can have a back end, and on this back end I can program this that says, hey, we're going to establish a new tunnel to this, and I would have digital certificates associated with it, and this back end could just be a self-signed certificate. Normally over here you're going to use what's called a publicly available CA or a trusted CA. That means if GoDaddy.com or Thought or VeriSign says, oh yes, this is evilhackerempire.com, they can go in, check with whoever the CA is. We'll say that I got a certificate from GoDaddy, and they can pull that down and find out, is the certificate still valid? Also, you have what's called a certificate revocation list. Has it been revoked? And then I can grab the public key. I encrypt with the destination's public key. So if I'm trying to get it to here, I grab the public key from, we'll say, VeriSign. They encrypt it with that public key. It goes here. This has the private key. It decrypts it. Then when it wants to re-encrypt it this way, I could have a public key here, a different one. I would have a private key here. I would install the public key on the encryption device. It will use that public key just to encrypt it, and then it uses the private key to try and decrypt it. And then it decrypts it, and then away we go. Now, you can also have these. So when it does the encryption, because it's going to handle this, you could just say, hey, I just want it to be clear text. It just depends upon what you need. One of the things that we're trying to do, and Microsoft's trying to do, and security is trying to do, and everybody's trying to do, is just assume that we're penetrated. Just assume we have malware. Assume that your administrators are writing their name and their password on a truck stop wall. So just assume that everybody is penetrated. And what we want to do is we want to reduce the blast radius. We want to eliminate as much as possible any of these bad effects. So by going in and doing front-end encryption and then doing back-end encryption, if I do have some malware or I have an employee that's a little less than gruntled, they're disgruntled, they're going to try and maybe sample that stuff, or maybe there's malware that's trying to sniff it. It's encrypted, so good luck with that. They also have this thing called MACsec. We'll be talking about it later. It does the same thing where we encrypt it into the device, examine it, decrypt it, examine it, and then re-encrypt it, but it's at layer 2. So every hop along the way, everything above layer 2 is going to be encrypted. The only thing that I can see decrypted is a source and destination MAC address. That's called MACsec. It's very, very powerful, but again, it follows that zero trust model. We don't trust anybody, but the reason that we decrypt it inside the device is so if we're using like a layer 7 firewall or something along those lines, or we're doing content examination, it would be able to pop it open. That's what this bottom thing down here does. This is for content filtering. This is where you could have it look for words. You could have a white list of websites. You could have a black list of websites. You could look at proximity of stuff. It can go in and say, oh, these look like credit card numbers. And so there's all sorts of different capabilities, but it's actually opening up the packet and opening up the segment and actually opening up the data and looking around inside. So, and again, the capabilities are really going to differentiate or differ based upon where this is. Now, both of these can be done visibly, where you have an IP address and away it goes. A lot of times this would be done as a network virtual appliance. And then I can have this running in a virtual machine. Up in Azure, you can do that, where you just say, hey, I want to do a network virtual appliance. And you make it so that all of the traffic has to stream into that network virtual appliance. And then once its hygiene is met, it's allowed out. But I don't tell anybody that it's there. You don't discuss security unless they have a need to know. One thing that drives me crazy is they'll say, oh, how did you do this really cool thing that we've been trying to do? And they go into great detail. Oh, yeah, we did this and this and this. Well, you're giving a recipe on what you did, and it tells the bad folks, oh, this is how we got found out. And they're like, oh, we were so clever. Ah! And then the next time they can't do it because everybody knows. you don't talk about security. You really, really don't, with especially the specifics in your environment, because nobody else has a need to know. And you don't want to just let that stuff out. So very, very good stuff. And again, be aware of the picture. Be aware of the picture. Now, the next one that we have is an analog modem. This is a modulator-demodulator going from digital to analog if you're using the digital subscriber line, which is a really old technology, with a scorching 128 kilobits per second. Woo! That's really massive. But it uses a phone line. And with this DSL, on their phone line, we have to do multiplexing. And we do that with frequency division multiplexing, so we have different frequencies. And what we do is if I just have regular phones and things, and it hears that, it's not going to work. So we would put on these passband filters, and we put them on all the other devices. And what it does is it filters out the Ethernet stuff, the digital stuff that we're sending, and so they just get the pure analog phone stuff. But on this one, we would plug it directly in, and then it would induce our Ethernet over the phone line. So analog modem. Now, they also have digital modems because a lot of times people use voice over IP. That's a little bit different. However, they both may use RJ11 jacks. And so if you plug an analog modem into a digital phone, the wiring might be a little bit different. And on a good day, it would just blow up the modem. On a bad day, it would blow up the voice over IP PBX gateway, which would be a bad thing. Bad thing. And these are layer 1 devices. They don't have any really, the stream is just layer 1. It just sends it right out. Another device that we have is a packet shaper. And what a packet shaper does is it would go in and it would do rate limiting. And if I just run this packet shaper in here, what it's going to do is it's going to identify important traffic. The way that we can identify important traffic is, of course, we tag it, say, ooh, this has a higher priority, let it jump ship. But it's not going to just make bandwidth out of good intentions and error. It doesn't do that. We can't increase the overall total available bandwidth. But what it'll do is it'll slow down the traffic that is not as important, and it'll allow the important traffic to jump ahead. And so the important traffic has a higher priority, less latency getting through the device than the non-important traffic. And that's just a method of doing it. The big point to remember with this is that you have to have something that differentiates it. And hopefully you can even have it automatically tagged as far as, oh, this is important stuff. For example, if you have a switch and you're using one of the ports for voice, you can tell that voice port, hey, I want you to tag that with a quality of service or some other tag, some metadata that I can use to differentiate so that I know that this has an elevated priority as opposed to, you know, Bob trying to stream the latest version of Rick and Morty from HBO Max. Who knows? So it allows you to do that. If we're going to go in and we are going to use a virtual private network, a VPN network, we also have a VPN concentrator, and it's really it's real similar to the encryption decryption, but the encryption decryption box is just a box that does encryption decryption. With this VPN, it is specifically designed for remote access, and there's all sorts of different VPNs that you can use. You can do SSL tunnels, you could go in and do IPsec, layer 2 tunneling protocol. I mean, there's just piles and piles and piles. And instead of having to have a dedicated server who's also, you know, your DNS server and this, that, and the other, this is dedicated hardware, so it's going to be really fast, and it'll be able to handle a heck of a lot more connections to your virtual private network than what you would normally be able to do with like a server. It gets overly saturated. So what we're going to do is we're going to go in and pull the stuff out. Now, Dan had a question. Is this like an advanced IDS, IPS? The content filtering really, it's sort of like an IDS, IPS. I mean, it just depends on whether it's able to do things. Normally, with a content filter, if you have stuff that's not supposed to be there, it just doesn't forward it through. So that could be sort of an IPS, IDS. You can have it notify you, just depends on the capability. But for the exam, we're not going to be calling this an IDS, IPS because that may be one of the options. And it's not. It is a content filter. So they'll say, hey, I want to be able to go in and on the fly, on the wire, be able to say, oh, you can't have this because it's got, material that's inappropriate. Or, hey, you're sending out credit cards. Nah, that's a bad thing. What would I use? And if they say IDS, IPS, content filter, or a load balancer, the answer is going to be content filter. So even though you're going to find a lot of things do stuff real similarly, and that's one of the cool things that I get into is most of the changes are just where did they move the button to do the thing that I want to do. That's what OSI did. They're like, instead of having it in one big pile, let's split it up into separate pieces, and then instead of having to change everything every time, we can just do it in segments. Same thing here. I can go in and I can just modify this, and I don't have to change everything else out there. Media converters, we've already talked about these. So questions and answers. What's this guy? Chat it in. Is that Ethernet to token ring? Is that multi-mode to single mode? Is that single mode to Ethernet, multi-mode to Ethernet? Is it fiber to coax? What is it? What is it? What is it? What is it? It is Ethernet to fiber, but is it single mode or multi-mode? Single mode or multi-mode? Yeah, this is single mode guy here. This is the multi-mode guy. So this is multi-mode to Ethernet. Multi-mode to Ethernet.